Hello, I'm Mike McCulloch. Did you know that you can derive Newton's gravitational law from quantum mechanics if you add in some knowledge of horizons? Well, you can, and I'm going to explain how to do it now. So, obviously you start with Heisenberg's uncertainty principle. So this says that the uncertainty in momentum times the uncertainty in position has got to be greater than or equal to h bar over 2, which is a very small number, Planck's constant over 2 pi over 2. So I'd like you to picture two Planck masses. So we'll assume we're using Planck masses for simplicity, and also because this method only works if you assume Planck masses, that they are the important things, because that's partly based on the gravitational constant which comes out at the end. Okay, so we have these two Planck masses orbiting each other, close, let's say close together, some distance d apart. And the interesting thing is that their uncertainty in position on the outer side of them, facing infinite space if you like, would be very large. But their uncertainty in position on the side facing each other will be much less. So here we can start bringing in quantized inertia, and we can say that the uncertainty in position dx is equal to the distance between them, d. We can also say, and we can assume this is an effect of virtual photons under radiation, that the uncertainty momentum is equal to the uncertainty of energy over c speed of light. That's because for photons and radiation, E equals pc. Okay, so we have this formula now. Now we can say that the energy is equal to the work done. We can define it as work done, so we can say that's force times the distance. So that's the distance the two masses have been separated from each other. That is the work done. So we get this, and then this is for a couple of Planck masses, but we want it for two larger masses. So in order to add all these Planck masses up, we multiply this formula by m1 times m2 divided by the Planck mass squared. And then it's not as amazing as it may seem, but it is true that h bar c over the Planck mass squared is equal to the gravitational constant. That is what it's defined as. So you'll see that here we get Newton's gravitational law from quantum mechanics. So the appearance of G here is not so surprising, because that comes from our assumption of using Planck masses, that these interactions take place between Planck masses. That's where G comes in. But nevertheless, this is the form of Newton's classical gravitational law from quantum mechanics and horizons. It's not the relativistic version, but it's pretty close. Okay, so I hope you've enjoyed this short, and I look forward to seeing you tomorrow. Goodbye.